activation functions. We mentioned the softmax, soft sign, and relief. So we mentioned all the activation function that we have, and we've mentioned the issues of having a vanishing gradient problem, which we do not find when we're using the radio. But as we're moving along, we're going to see how we're going to be using this activation function, which are used in neural network. Okay, so and we also started with normalizers. So in deep learning, we have what we call normalizers. Normalizers, what's the purpose of normalizers? The purpose of normalizers is to make sure we can quantify or we can limit certain parameters for us to try and avoid any issues such as overfitting problem. Okay, so especially when we're dealing with large numbers of parameters that need to be used in our neural network. Okay. We mentioned the 4 type of normalizer that will be used. The first one will be to add a constraint to the parameters, such as L1 and L2 norm. So can anybody remember, first of all, can you give me an example of a parameter? Can you give me an example of a parameter? Can anybody give us an example of a parameter? This one. Anyone should know at least one example of a parameter. An example of parameters in deep learning. As you remember again, what was the difference between the parameters and the hyperparameters?
Isn't it that parameters are set by the model and then hyperparameters are determined by the developer?
Okay, that's good. So what example of parameter can be set by the model itself? Give us an example. Okay, so we have the weight that is being used, which we know the weight is just the weight of the connection between neuron in a neural network. So the weight is set by the model itself. So those are parameters. This is why when we add the constraints to parameters, we can add the constraints to the weight. So we can limit the weight and say the weight can only be a value between a certain number. We, instead of us adding a weight that can be any value. So that is adding the constraint there. Okay, so and when you think about example of hyperparameters, that are settings that are set by the developer themselves. So such as you have the numbers of layers, numbers of hidden layers, numbers of neurons, activation function, which activation function is going to be used. So those are hyperparameters. Okay. Okay, so the first normalizer that we're going to use in order for us to avoid an overfitting problem, we're going to use a constraint to the parameter. Okay, so those type of constraints we can have, for example, the L1 and L2 norms. Okay, so those, what is L1 and L2 norms? Okay, first of all, we learned we're gonna add the constraint, or we can expand the data, but we spoke about it yesterday. So the constraint that we're going to add, so basically this can be considered to be like a penalty parameter. All right. So what we're going to do with the model is that we're going to penalize the model for reaching certain values. So uh, so we basically create the constraint. So this is an example of a constraint that we're going to have there. So we're going to look at something, for example, like the weight. We say, okay, the weight can only be a value below a certain amount. Okay. Right. So basically, we're going to have the L1 and L2 constraints that we're going to add there. So what is the L1? The L1 constant is represented this way. Okay. So the L1 constraint uh, is basically going to give us what we call a measure or a magnitude of a certain vector. And the vector is composed by the input and the output that we have. So we're basically going to limit that. And then we have the L2 norm, which is also another constraint, which going to be represented by a different formula. Remember, guys, what I said, you don't really need to memorize this formula. Uh, but this is the formula behind the code that you're going to write. Okay, so we have these constraint parameters that will help us avoid overfitting problems. Okay, so the second one would be a data set expansion. So if we were dealing with data that are giving us problem, when you have an overfitting problem, it means that your model has been trained properly, but you did not have enough data. So your model is showing you as if everything is perfect, but you did not. An example that I can give you is, let's say you're trying to get um, a, a model to recognize, to distinguish between animals, right? And then you only test with 10 pictures. And then when you test with 10 pictures, you train with test 10 pictures, and then when you're testing your model, you realize that your model is being accurate. So you may think that your model is accurate until you put it in a real life example, and then it cannot perform well. Why? Because it was just overfit. There was not enough data for that model. All right. So I remember when I was on Sunday, I was in a spa, and in that supermarket, on the side, you see the side where you can buy. Let's say you buy things like onion, tomatoes, and sometimes there need to be someone working there so they can measure it for you and give you the price. But in that spa where I went, there was no one working there. Solve yourself. You just take the whatever. If it's tomatoes, you put it yourself. It's in the plastic. You put it on the scale, and then there was a screen that will show you that this is tomato. This is the price, and then you just click on the screen. It prints that small paper, and then you put it on your plastic. So when I got there, people were just taking the stuff and move, but I stopped a bit. And then I look at it, I'm like, that's really, really brilliant. So I had to check and see, okay, there's a camera below. And actually, I was with someone who never understood. The person asked me, how does this machine knows that this is tomatoes, these are bananas and everything? And I was like, no, there's a small camera there that will identify, which is using deep learning. It has been trained using deep learning to recognize different stuff in the shop. So every single fruit or vegetable which need to be put on that scale the machine has learned from it. So this machine knows about those type of things. So that's why it can be able to identify them and give you a certain price. So now when you're training the machine like that, you need to make sure you have enough data to train the machine, or else you may end up having an overfitted model. Okay, so that's why one of the normalizers that can be used is the dataset expansion. So dataset expansion, it means that we are adding more data to our data set, or we are transforming those data. All right. So basically, we can add more data, or we can transform the data. What does it mean to transform the data? It means sometimes all you need to do to your pictures is to change the size and make sure you have all the sizes that are the same, or make sure that you have certain pictures where if you're dealing, for example, with an image recognition system, you want to have also pictures that are in a different direction. So maybe your pictures are upside down, something like that. Okay, so you want to try that because that can also help with getting the your model to be able to identify pictures easily, because your model has been trained to identify pictures even if they are not aligned straight, even if they are bent to a certain angle, your model is going to be able to detect that. All right, so a common method of object recognition field is to rotate or scale images. Okay. Okay, so when you're dealing with speech recognition, you can just add random noise to your training so the system gets used to it. Okay, when you're dealing with natural processing, natural language processing, where you're dealing with certain languages or certain model that has to do with word and everything like that, you need to replace words by the synonyms so that the system understands different meaning of different word and the synonyms used in a certain sense. Okay, so those are the dataset expansion. And another normalizer, the third normalizer is what we call the dropout. Remember yesterday I mentioned the dropout means sometimes we don't need to use the whole neural network. Sometimes in training, what you're going to do, you're going to introduce a dropout, whereas the model is training, you tell the model to drop out a certain part of the neural network. So if this was the network, it's going to maybe drop out, for example, this was the network, original network. Instead of having 4 nodes there, we're just going to use 2 first and see where we're getting it. And then the model will try again and train it with first layer with 3, and then it get that. So these are dropout methods, which are widely used to try and solve the issue of overfitting and that. Okay, so that's what we're going to do. So basically, these dropout methods, we're going to discard certain inputs during the training process. Okay. So, and basically you need to understand that the dropout will combine all sub-network results. Okay, so if we drop out here, this network give us a certain result, this one give us another result, this one give us another result. It's going to combine all those results and obtain a subnetwork by randomly dropping input. Okay, all right, so and then the last one would be the early stopping. Remember I mentioned yesterday that sometimes when we're trying to train the model, what's the numbers of time that we are training the model is what we call an epoch. So if when we're going to start next week to create a model by coding a model, you need to realize that whenever we're going to, in our code, when we're going to mention epoch, you must understand this is a numbers of time we want the model to train. So if you set this to 5, your model is going to train 5 times only. set it to 1,000, it's going to test 1,000 times. Right, so remember that. So now, as we starting from the first epoch here, let's say we want to train. We, in the beginning of our training session, we choose 1,000. So 1,000 times, the model needs to train, learn from the data. And the first time we realize that we have a training error, which is really high here. As the error is dropping now, the more we are training our model, the more our error is going down. And then we get now to a point where, at this point now, the error is minimal. But then as we continue, let's say this was at 700 epoch, but we still want to get to 1,000. But now we notice that from 700, that's where we had the lowest value. As we continue, we now have an increase of the validation error. So now we have this error here. So we know that we just have to stop training from here. So basically, we're now going to change our training model to only train 700 times, not 1,000 times, because 1,000 times will give us the wrong model. So this is the method called an early stopping. Okay, so we got the normalizers. Guys, we got 4 normalizers. Can you guys tell me what are the 4 normalizers? What are the 4 normalizers? We just spoke about the 4 normalizers. Anyone can give us any of them?
It's L1, L2 regularization, the dropout, expanding your dataset, and early stopping.
Perfect. All right, so we have those normalizers. So we are now sure we have the normalizers. What about the activation function? What do we have as activation function? What do you guys remember?
We have the ReLU, the sigmoid, I think the softmax also.
Yes.
I think there's other ones, sign something, I forgot.
Yeah. All right, so that's good. We have the 10H as well, the soft sign as well. All right, so okay, so those are activation function. What do activation function do? They actually introduce a non-linear function into a linear function. What does activation function do? They can they activate all the node in a neural network. Normalizers, what normalizers do? They try to create, solve a problem of overfitting by managing all the parameters. All right. How do they manage all the parameters? They can manage the parameters based on what we can do with the network, such as adding data, that is a data expansion, or we can do a dropout, which means we cutting down certain part of the network while we're training, or we can do an early stopping, which means that we stop training before we can get to the last epoch. So we stop training as soon as we have the minimal loss. All right. And then we have the L1 and L2 norms, which we can use to manage the range of our parameters. Okay, so the next one will be optimizers. Right. So what are optimizers? So basically, you need to know that as we're training our model, we use certain methods such as the gradient descent algorithm. Remember when we used the gradient descent algorithm, we had 3 types of gradient descent. Guys, do you remember? We had the BGT, batch gradient descent. What's the next one? What was the next one, guys? Guys, what's the next gradient descent method? We have the back gradient descent. What else do we have? We have 3 of them. So we have the batch gradient descent. We have the mini batch gradient descent. And what's the third one? We have the stochastic gradient descent. All right. So now these are methods that we use in order for us to reduce the loss by changing. So this system, these functions are going to automatically change the parameters, the weight, until we get the weight that gives us the lowest loss. Okay, so this gradient descent method can be encapsulated into object called optimizers. So these object optimizers are just an implementation of gradient descent algorithm. So why do we encapsulate them into optimizers? It helps us to accelerate the algorithm convergence, to prevent jumping out of extreme values, so you don't want to be training your model and then the values of what you're getting is really jumping. So we want to kind of control it. So we want to control how the values are behaving. So to avoid jumping out of local values, we use optimizers. And then it also helps to simplify parameter settings, especially a setting such as the learning rate. The learning rate determine actually how fast or how do you want your model to be learning, right? But we're going to talk more about it as we moving along, right? So these are example of optimizers. We have GD optimizers, momentum, Nesterov, other grade, other delta. So all these optimizers are different optimizers. So you will choose which optimizer to use as you're training the model. Okay, so they have different advantages and disadvantages. For example, you have the momentum optimizer, which has its own advantage. It can enhance the stability of gradient correction direction and reduces mutation. But the disadvantage is that the learning rate and momentum alpha need to be manually set. So that's the problem here, because now as you're using this optimizer, if you're using the momentum optimizer, you actually need to set what's the learning rate. The learning rate is usually a value as small as maybe 0.0001. It can be the learning rate. But again, remember, this is an hyperparameter. It's an hyperparameter. Why? Because you're setting it yourself. So when you look at the method that we learned recently, when we learned about hyperparameter search, right? Like those random search, grid search. So when you use those search, you can get the right learning rate to use. Okay, so, and then you have the other grade optimizer. You have the RS Proc optimizer. So you have all these different optimizers that are performing differently. Okay, so type of neural network. Guys, we have a few types of neural network, but it will depend on the scenario. It will depend on what you're trying to achieve. So if you're dealing, for example, with an image recognition, you're dealing with images, you have certain neural network that you're going to use. If you're dealing with sound, you have certain neural network that you use. If you're dealing with something else, whatever you're dealing with, you need to use the right neural network. Okay, so the first one that we're going to see will be the CNN. The CNN is the convolutional neural network. This is the most famous neural network. Why is it the most famous neural network? Because it's a neural network which is used for image processing, for everything that has to do with images, identifying images, and all those things that we know today. The CNN is the neural network that is used. Okay, must remember it's a feed-forward neural network, which means information goes from input layer to output layer. Okay, so the neural network is very good in image processing. So now, the structure of the convolutional neural network is that the convolutional neural network is built in such a way that it has certain part of the network are doing different actions. So when you're building that network, when you're coding and you want to use CNN, you need to mention every part of the network. So it includes a convolutional layer. So one of the layer need to be a convolutional layer. There's a way that you build a convolutional layer, which we're going to talk about it as we going to go to practice next week. So the convolutional layer is a layer that has to be part of the CNN. And then we have a pooling layer, and we also have a fully connected layer. Okay, so CNN is very, very, very important. Okay, so the main concept of CNN, we think of, when you think about, when you look at even in your own culture, you realize that the way you see the world is mostly based on the way you see the area where you're living in. So your own environment will determine the way you see the world. So that's where the main concept of CNN comes from, because we don't look at a picture as just the full image, but we look at the picture as each pixel of the picture is playing a role in that picture. Okay, so which means that if we're dealing with an image recognition, if we're dealing with an image, if we use CNN, the way CNN works is CNN does not need to know that this picture is a picture of an apple for it to identify this as apple. It doesn't need to know the global, to have the global view. It only needs to know the local image. What is the local image? Is this small pixel. What does it represent? This one, what does it represent? This one, what does it represent? This one. So each pixel here is what the CNN is interested into. And after it analyzes everything, then the CNN will be able to put everything together and identify this as an apple. So that's the main concept of CNN. Okay, so now how the CNN is going to work, we're going to look at all the type of layers it has. It has a max pooling, pooling layer, it has a convolutional layer, and it has a fully connected layer. So now an example here of the architecture. So you're going to input an image. So this is the image that you input, but the CNN does not care about the global picture, but it looks at its pixel. So each part of this picture here represents something. It represents an information that we have in the input layer. You understand? So now, based on that information there, the convolutional layer is the first layer that we take it into a pooling layer, okay, until we get to a fully connected layer. So we have, after the fully connected layer, then we can be able to determine if this was a bird, a sunset, dog, cat, or whatever we want in our output. Okay, so as part of, it's now going to have what we call a kernel, which will take the input layer and convert it into a certain form. It's going to map it and create all the feature map that we have. Remember, here on this picture, for example, so if we have 28 pixels by 28. So we're going to have in the first layer, we're going to have every single pixel there. So 28 by 28, that's 784. So we have 784 input layer. And each layer and each node will take a value that will determine how dark or whatever is the shade there do we have in the first node or in the first pixel, which will be a value from 0 to 1. And it does the same with every single pixel until we've created the whole picture, right? So this is an example here. We have an image, which is a 5 pixel by 5 pixel. So the first pixel here, the image is giving us 0, right? So let's say this look like an image that look like this. I want to show you. Let's say this is the image that we have. Okay. So this is the image that we have. The image is full of colors. I don't know if this is a boot or what, whatever image this is. As you can see on this picture, so this can be the whole frame of the picture, and then our image, something like this. Okay, guys, so try to picture as if this whole image here as a shade, right? As a certain color. So we look at the picture. This is the picture of the object they gave you. So as you look at this object here, so each part, so this part, for example, this pixel here, if this is a 5 by 5 pixel, so this pixel here, it was an empty, so it does not have any shade, so we're gonna give it 0. So basically here we're gonna have values from 0 to 1, which can be 0.52 or whatever value you have based on the shade that you have. So in this case, we have something maybe as a fully black or full red. This is full red over full white. Then here what we're gonna have, the first pixel give us an activation of 0, the second one 0, so we have this. So this is what the image gives us. And now we're going to do what? We're going to introduce a bias, which is 0 here. So now this is what we call a filter. So now this filter will be applied to these images for it to give us a feature map. So how does it work? We have so why this thing is not moving. Okay, I'm not sure why it's not moving, but what we having here, let me just change the color. Okay, what we have here is this pulling here, this filter here will be applied to this. So it's going to occupy that value there. So it's going to occupy that value, and that value will give us the value here. And then it take again the other part, give us the value here, and it take the other part, give us the value here. So that's how it's going to create a feature map. So remember, a convolutional neural network will have a convolutional layer, which is basically using a convolutional kernel, which will use a bias with an activation function. We're going to have a certain output. Okay. And then the pooling layer, how will the pooling layer work? The pooling layer will take the whole map. Okay, so remember here, we're going to get this mapped feature here. So this is what the convolutional layer will give us. So now that we have this map here, so an example I can give you here. So when we have this and that, it gives us the value here. Okay. So, and then we have the convolutional kernel, which is what I just showed you there. An activation function, we're going to have the output, and then we have the output tensor, which we're going to use in the rest of the program. Okay, and then we have the pooling layer. The pooling layer will take that mapped image that we got there, and then it's going to do, depending on if you're looking for the maximum, the max pooling operation or the average. So if you're looking for the max, so we now when I look at this, for example, this area here, from this pooling here, so we take the first area, which is this one. It's a max pooling. That means we look for the maximum number, the highest number. 56, we go here. And then we do the same thing there. The highest, okay, so we do the same thing here, the highest 255. We do the last one, the highest 32. So that's what we have here. So we finally turn it into that. Yeah. Okay, and then we have a fully connected layer. So a fully connected layer is essentially a classifier. So this is going to classify and tell us if we what category we are getting from whatever category we wanted. So generally, the softmax function is used as an activation function of the finally fully connected output layer that will you use to combine all local features into global features and calculate the score for each type. So we're going to have, if you are trying to determine between mangoes, oranges, and tomatoes, so it's going, this softmax will be used here. So this can give you maybe 0.33, 0.6, 6, and then we have 0.01. So we have these probabilities here. Okay, so that was the CNN. Remember, what to remember, the CNN is used for image processing. The CNN as in its structure, it has convolutional layer, it has fully connected layer, and it has pooling layer. All right, that's how the neural network is. So, and then we have the RNN, recurrent neural network. So this neural network is used mostly when we have a scenario where the events are recurring, where you have events that require a certain memory from what has happened before. All right, so that's how the RNN works. So if you're dealing with images consisting of like you're dealing with audio consisting of clips, you're dealing with videos consisting of images, sentences consisting
I'm sorry,
of
sir.
words.
Can I ask something?
Yes.
Can I ask something before we move on to the RNNs?
Yes, you can.
Is the size of the feature map determined by the kernel?
The size of the feature, I don't get it. What you're saying?
I saw the size when you were demonstrating back there. The size of the kernel was the same size as the feature map. It was a 3x3, and it was what I don't know if it's multiplied, but it was a 5x5 and a 3x3, and the feature map was a 3x3, same as the kernel. So I'm just asking, is it always the fact that the kernel determines the size of the feature map?
Now, there's a lot of things that will really determine the size of the feature map. Because remember, you also need to know what's. Let me just go back there. We also need to know what was the size of the input layer, right? So here we have a 5x5, okay, and then we use a 3x3 kernel, and then we can map into 3x3. But if this was bigger than 5, so let's say, for example, we had another 3, or if it was bigger than that, it means that this will have to go there first, give us a value. It goes there, give us a value, it goes there. So we'll surely have something with 4 here. 1, 2, 3, 4. You see, the size would have changed depending on how the input size is. You understand? So the input size, even if we take this size of 3x3, but if the input size is bigger than that, we're going to have a featured map which is bigger than that. Do you get that?
So there's no mathematical way to determine the size of the feature map, sort of like how we do it when we're multiplying matrices.
It's the you can actually get it as a, so if we have to understand it as a formula, normally we have it should be, if I'm not mistaken, something like the input size, depending on the size, the input size minus, so input size minus the kernel size plus 2 over what we call the padding. The padding is just the amount added to the input data that we have there. And then everything should be divided by another value called the stride plus 1. It's just a big formula to actually determine the feature map that we're going to have. But you can visually see it if you look at what you call this. You can visually see it if you look at a very small image such as this. It's just 5.5. We can easily see the kernel, type of kernel we want for that. We can easily see that. But if we have a very big picture here, it's not really easy to see that. But there is a formula that will determine that. Okay. So it's
one last question.
Yes.
On the max pooling part, do we use a kernel also?
I don't get you.
When we're extracting the maximum values, we're using a kernel.
Now the max
or something
pooling,
that
okay.
or something that's maybe similar to a kernel.
Yes, yes. So basically, it's also another filter that we use, but it's a different method. So basically, we use also kind of a kernel in a max pooling, but in this case now we're going to use it in such a way that we're not really multiplying by other values, right? It works a bit different, but the value that we have from this map. Remember, this map has been created from the previous layer. You understand? And then from that layer, we just taking the maximum based on each part of it. So the kernel here we're looking for to want to map it into a 2 by 2, right? And then we can take it from here. So in each one, so if this map was bigger than this, we're not gonna do it in this size. Again, when you programming it, you can easily choose those as parameters, hyperparameters. I mean, I don't know if I've answered to your question.
Yes, you have. I think I get the idea.
Yeah.
Thank you.
We even in the max pooling, we're also using a kernel, or also called a filter, right? But in this case, that kernel will just scan the input features and then map them into a certain by looking at just the maximum value for each kernel region. So the kernel will take this region first, gets the maximum feature. I mean this. And then it's going to take this area, it's going to scan this area and get this. But with convolutional layer, here the kernel, what it's going to do, it doesn't just take any maximum or whatever value, but it's going to take this, it has a bias. It has another metric that it's going to take and multiply it by whatever value we have there. Okay, so that's how the map is created. So basically here we're going to, for example, for the first one here, we're going to have this will go here. And if it goes there, you can see we're gonna have this 1 times 1 times 0 times 1 times 0 times 1 times 0 times 1. So that means we're gonna have there 1 plus this one is 0. And then here we're gonna have plus 1. Okay, this one we're gonna have 0. Here we're gonna have plus 1. Here we're gonna have 0. Here we're gonna have 0. Here 0. Here we're gonna have 1 plus 1. So you can see 1, 1, 1, 1. We have 4. So this value here will be a 4. Okay. Do you get that? Do you get the idea?
Yeah, you were multiplying corresponding indices and then adding them. Something like that. I can't explain it, but I think I get it.
Let me do this. Just that the next slide was supposed to show us that, but I don't know why it went there. Okay, let me just change the color and show you that. Which color is going to let's say blue. Okay, so basically how this is going to work is that this filter here, this is a filter, a 3 by 3 filter, which is taken for this scenario. If this image was bigger than this, the filter as well, we're going to get a size that will make sense with each part of the picture. So here we have this filter here, which is taken here. So the first time we take it here. We take it there, so we're going to have times 1 times 0 1, 0, 1, 0, right? I'm taking this there. This is 1, this is 0, this is 1. Okay, so the first one was 1. 1 times 1 is 1. And then plus. The second one here, it's times 0. That means we're going to have a 0. And then the third one, we have a 1. 1 times 1 is 1. Plus, we go down here, 0, plus 1, plus 0 again. Down here, we have 0, 0, and then plus 1. Okay, you understand that? So this is 1 times 1, give us 1. 1 times 0, it's 0, so we didn't put it. So in total, we have 4. So first scan of the kernel here give us a value of 4. And then we take the second one. Second one will be here. We do the same thing. 1 times 1, we have 1. 1 times 0, we have 0. 0 times 1, we have 0. And then 1 times 0, 0. 1 times 1, 1. We have another 1 there. 1 times 0, 0. 0 times 1, 0. 1 times 0, 0. And then 1 times 1, 1. Plus 1. So the total here we got 3. So this is the value here, 3. You understand? So same thing. And then the third one, we're going to take first. We do the same thing. 1 times 1, we have 1. Plus what? 0, 0, 0. And then here, 1 times 1, we have 1. And then here, 1 times 0. Here, 1 times 1, we have 1. 1 times 0, 0. 1 times 1, we have 1. So total here, 4. Here as well, we have 4. And then we move to this other section here. As we can see, 0, 0, 0, 0, 0. This one as well. And this will be 0. And then here we're going to have a 1 plus 0 plus 1, 2. So we have a 2, 4. Okay, I went to the bottom straight. So we're going to have a 2 here. So if I take the middle part there, the middle part will give me the value here, which will be 0, 0, 0, 1 times 0, 0, 0, 0, 0, 0. Let's go here. 1 times 1, we have a 1. We have a 0. We have a 1. That is 2. So this part is going to be as well 2. Can you see? So that's how we're going to fill up the whole feature map. Now from that feature map, when you look at the image like that, the feature map, that's how from the featured image there, we're going to now apply another kernel or a filter, which is using a pooling, which is a pooling layer. We're going to look for the max pooling. So the max pooling will scan each section there and get the maximum. All right. And then we have the fully connected layer. All right, guys. I think time is up. Tomorrow we're going to start with recurrent neural network. Is there any question before we could call it today? Any question? Any question?
I have a question about the optimizers.
Okay.
Are there certain optimizers that are recommended for CNNs?
It will also depend, right? remember what we said about optimizers. We have advantages of using certain optimizers and disadvantages. You have certain optimizers that require you to have all those hyperparameters that you're going to have to save, which will require you to have a certain experience with that, right? So when we're using CNN, for example, you can use an Adam, you can use uh, uh, different stochastic gradient descent, which we use with certain momentum optimizers, okay, such as the RMS prop, but it will depend as well on your scenario. But the most used, people usually use Adam optimizers. Yeah, people use Adams. Why? Because even if you're using the RMS prop, because the Adam will combine the RMS prop and the momentum optimizer. So it's basically an optimizer which is kind of combining two different optimizers. So Adam is really a popular choice of optimizers. Yeah.
Okay, thank you. And one last question. Are all CNNs feed forward?
The CNN, yes. The CNN, the whole point of CNN is it's a feed-forward neural network, but we use back propagation to look at errors, right? So basically, if you're having some errors in the way it works when we're reducing the errors, when we want to find the errors, when we want to get the error, we're going in a back propagation direction. So but usually all CNN are considered to be feed forward neural networks because the data will flow from the input layer to the output layer. So that's why they call them feed forward, because we're going to have an input layer, we're going to have hidden layers, and then we're going to have output layers. Okay. Any?
Okay. Thank you, sir.
All right, guys. I think you can turn on your camera so we can just get all right, guys. I guess I will see you tomorrow at 5:30. But anyway, for the recording of different videos, I've uploaded them on YouTube. I'm going to send the link to the group, and then you're gonna access everything big data and AI as well. All right. Thank you, guys. Have a great evening.